to do today, I might ask for another class, okay? Because I feel that the harmonic oscillator is something that you should understand, and we should not cut corners. Okay, so this is basically the icing of the cake for the whole course. Okay.
Augustine.
Okay, so
Fine by me.
yeah, so let me share the screen. So let's just carry on here. Okay, so we were discussing the harmonic oscillator, and we wrote down the Hamiltonian, which was p squared by 2m plus half kx squared. Okay, and we showed that the expectation value of h is greater or equal to 0. And from that, we figured out that all the energy eigenvalues that say h psi I ei, maybe using n is a better idea, that's a convention, that all the energy eigenvalues en are positive, definite. And this comes from the fact that the expectation value of an operator has the interpretation that it summed over all the eigenvalues times the probability that that eigenvalue is going to occur. And since these are positive numbers, and we can choose h to be in, say, some particular to be expectation value in a particular eigenfunction, in that case, we will get en, right? So, this gives us, well, there are different ways of, the fact that this is positive also implies that these are positive. But of course, some can be negative, some can be positive. So I think this is a cleaner, argument. Okay, so any questions about that?
No, sir.
Okay, so why is this positive? Well, any operator, say, which has, okay, well, the argument that we use, say, if I were doing p squared acting on psi, this thing, then we can write this as p dagger of psi, p of psi. This is the definition of Hermitian conjugate. But p is a Hermitian operator. So we can write this as p of psi, p of psi. But this is some state, say phi, and this is some state phi. And therefore, this is equal to phi comma phi. So the fact that the harmonic oscillator is quadratic, that its harmonic, the Hamiltonian is given by quadratic Hermitian operators, is the reason why it's a positive definite operator, okay? Just to give you the intuition. All right? So,
Yes, sir.
So today we will solve the Schrodinger equation in one way, and if we cannot finish the other approach, as I said before, I'll ask you for another class, and I think it's very important that we finish harmonic oscillator. So our Schrodinger equation, Schrodinger equation is minus h squared by 2m. And we are solving the time-independent Schrodinger equation. So it's d squared of psi of x dx squared plus half kx squared of psi equal to e of psi, right? This is the equation that we want to solve. So this is, yeah, anyway. So how do we do this? Well, we first, for the sake of convenience, we introduce a dimensionless constant, a dimensionless parameter to measure energy. So energy is going to be measured in units of half h bar omega. Okay. So the lambda is a dimensionless measure for the energy, right? If you're using this, so this we are going to call E naught, the ground state energy, we'll see. And then we also have the classical maximum amplitude A, and that's going to be h bar divided by m omega square root. Okay, so if and then I define x prime to be x by a. Then I express everything in terms of this guy and this guy. So if I rewrite Schrodinger equation now, I get m omega by h bar, and then inside the bracket, d squared psi dx prime squared plus lambda minus x prime squared psi is equals to 0. So this is just a rewriting. And because this is a non-zero constant, we can divide both sides by it, and we replace x prime by x. This is just a notation. This is not our original x, because we don't need x prime. We don't need the prime anymore. It's a relabeling. So if I do this, then my differential equation becomes psi d squared dx prime plus lambda minus x squared psi of 0, right? Or we can also write it as psi double prime plus lambda minus x squared psi equals to 0. So this is the differential equation that we want to solve. Okay? Any questions so far?
No, sir.
Okay, so this is a bounded potential. We saw that the potential looked like this. It's quadratic. So the potential is like this, right? So this means that this is x equals to 0. So this means that if we go all the way to infinity in one direction or the other direction, we would expect the wave function to go to 0, right? Because otherwise, the energy, the eigenfunctions will, the wave functions will not be normalized, right? Because this is what L2 integrability means. Also physically, we expect the wave function to, go to 0. We had this analysis before, right? So that the probability is going to be finite. Okay? So asymptotically, let's first try to solve the differential equation psi double prime plus lambda minus x squared of psi asymptotically. Okay? That is taking x to infinity. Okay? So in that case, we can ignore the lambda term, right? Then my equation becomes, this is proportional to some x squared psi, okay? Or this is equal. Okay, so it's easy to verify that, the solutions to this equation are some constant, some x to the power n is some integer, e to the power plus minus half of x squared. Okay, so you just plug that into this equation. Okay, but we see that only one of the signs here is going to make sense. Can you tell me which sign?
Minus.
Right, exactly. Right, so I'll leave it to you to verify that this is a solution to that equation, but we are going to take the minus sign. Okay, so the exact solution, we can say we'll have some form like this. There'll be a psi of x, and there'll be another function phi of x, which at large x will become like this, and then there will be e to the power minus half x squared. Okay, so this is going to be the form of our solution. So this is what is in the business is kind of known as an ansatz. Okay, so if I plug this ansatz into our full equation, which is psi double prime plus lambda minus x squared of psi equals to 0, then we get an equation for phi. And what is that equation? The equation is phi double prime minus 2x phi prime plus lambda minus 1 phi equals to 0. Okay, I'm not deriving this because I am assuming that you are able to do this. Okay, right? You're able to do this. Okay, now we want a non-singular solution, so we can try a series ansatz, series solution ansatz. Okay. So the series solution will be phi of x is equal to n goes from 0 to infinity, and there are some coefficient a n, and then there is an x to the power n. Why did we take n to be 0 or positive?
Singularities, I guess.
Right. Otherwise, it'll be a singular solution, right? And we know that if you have a singular solution, we'll have problem normalizing it. It won't, So, okay. So now, given this, this is something you probably learned in differential equation class, but it's actually worth doing it, okay? I love solving differential equations in the boring way. So psi prime of x, which will give us this term, that's going to be equal to n equals to 0 to infinity. There'll be n, a to the power an, and then x to the power n minus 1. Okay, so as you can see, the n equals to 0 term is not going to contribute. And then psi double prime of x is going to be similarly, n goes from 0 to infinity. There is n, and there's n minus 1, and then a of n x to the power n minus 2. Now we can put all of this into our differential equation over here, and we factor out the sum, and this is 0 to infinity. What was the first term? The first term is there's double prime. So if you have double prime, then we have n times n minus 1 an x to the power n minus 2. And then we have a term which is minus 2x phi prime. So we get minus 2n, and here we had an, and then we had x n minus 1, but there's a factor of x there. Because there's a factor of x there, this will be x to the power n. And then we have lambda minus 1 an xn. And this thing is equals to 0. So this is, we have converted our differential equation to a number of infinite algebraic equations. Okay? All right? So now, one thing we can do is the following. We can manipulate this a little bit. See that this is xn, this is xn, so we can just, we can just write this like this. I think, Nian, your microphone is not muted. Yeah. So can you, okay, I muted you. Okay. So this is an xn minus 2, and then we have minus 2n minus lambda minus 1 times an xn, and this thing is equals to 0. Okay. All right. So now the thing is that we know that the coefficient of all the x powers will be 0, right? Because they're all linearly independent functions. So, so we basically have x. So if I look at this series, I put when n is 0, I get from here x to the power minus 2. So that coefficient of that term is going to be 0. What is the coefficient? The coefficient is 0 minus 1, a0 is equals to 0. So this doesn't give us any information, right? Because both left-hand side and right-hand side are 0. And then we have x minus 1, which we get from putting n equals to 1 here. So for that, we get 1 times 0 times a1 equals to 0. Again, 0 equals to 0. But then we get x to the power 0, and there we get, how do we get x to the power 0? We put in the first term, n is 2. If n is 2, then we get 2 times 1 times a2 is minus 2, and here x equals to 2. X equals to 0 means this is 2 times 0. This is plus lambda minus 1, and then here a of 0. Okay, so here we get a useful equation for a0. Okay? So,
Sir, I think it's
so if you
minus
keep,
lambda minus 1.
yes. Okay. So this is awesome. Okay, good. So, and then if you look at the coefficient of xn, the first term is going to be, the value of n here is going to be n plus 2. So we put n plus 2, n plus 1, a of n plus 2, and that is going to give us equal to 2n minus lambda minus 1. Okay, so in general, this is the equation we get. And what is this equation? This equation relates this coefficient to this coefficient. This is what is known as a recursion relationship. So we can rewrite an plus 2, express it in terms of 2n minus lambda minus 1 divided by n plus 2, n minus 1, a of n. Okay, so this is the recursion relationship if you want. So what does it do? It tells us that if I tell you, say what A0 is and A1 is, then all the other A's will be determined by this equation, right? So, these are not fixed by A0 and A1 are not fixed by this, okay? So we actually get two classes of functions. So we get two classes of solutions. One in which A1 is 0, A0 is 0, and another one, A1 is 0. So the first one is A0 is 0, and that class of solution is going to be phi of 1. Let's call it phi of 1. It's going to be A of x plus A3 x3 plus a5 x5 dot dot dot. So these are odd functions, right? So we get a class of solutions which are odd functions. Of course, we can take linear combinations of these two different classes. So, and then the other class is when A1 is 0. And in that case, we write the solution as phi 0. And it's going to have A0 as a leading term, then A2, x2, A4, x4, plus dot dot dot. And these are even functions, okay? Okay, is that clear?
Yes, sir.
So phi 0 and phi 1 are linearly independent solutions. All right. So okay, next we are going to find by examining this series, the quantization of energy. Okay. So we saw that for bound potential, we usually get quantization of energy. Okay. And there are general arguments for that, although I haven't really given you the general argument. But here we will see the same thing. Okay. So let us consider two consecutive terms in one of this series. So consider, say, two consecutive, sorry, that's not how consecutive is spelled. Terms, and an plus 2. So we are taking the ratio of two consecutive terms. So this is the n plus second term, and we take the ratio with an xn term. Okay, so if I look at the coefficients, if I look at the, our recursion relationship, it gives you 2n minus lambda minus 1 divided by n plus 1 n plus 2 x squared, right? So if I go back and I look at these guys, we find if I bring this over to this side, and then, there are factors of x's, if I take those factors of x's, then this is what I get, okay? So now let's look at large values of n. What happens to this ratio for large values of n? So for large values of n, what do we see? We see that over here, this becomes the numerator, the denominator becomes n squared, right? And the numerator becomes 2n, right? So for large values of n, we see that the ratio goes over to, say, 2x squared over n. Okay, do you agree? So for large values of n, this is actually a, this is a convergent series, and asymptotically, then we can say that asymptotically our series looks like this. Sum over, this is asymptotically, okay? So although I'm putting n equals to 0 here, what I'm saying is that the series that I'm going to write down is what this series looks like asymptotically, okay? So this is a series where each consecutive term, the ratio of each consecutive term is exactly what we are looking at. But this series is nothing but e to the power x squared. Okay? And we can also write this as n equals to 0 yeah. We can also write this as n equal. Okay, I don't think I need the other information. Okay, so this is the asymptotic behavior of phi, right? So right. Okay. So remember the full solution. The full solution had phi of x and then e to the power minus half x squared, right? Remember that? Let's go back to the full solution, right? Minus half x squared. So this is the full solution. And so we found that the phi itself asymptotically, phi of x asymptotically, behaves like e to the power x squared, right? So when we put these two together, we have a problem. Psi is divergent, right? So how are we going to be able to solve this? Another thing, note that this analysis did not put any, this analysis so far, doesn't put any constraints on lambda, the energy parameter, right? So the way to solve this problem is to go back and say that, okay, what if in our series, the value of lambda was such that at some point, the series truncated, okay? Some point, the series truncated. In that case, it's, in that case, the asymptotic behavior will no longer be of this form. And, the polynomial behavior means that for large values of x, this thing will diverge quite dramatically, but nothing can diverge faster than the way this guy is going to go to 0, as long as the divergence is polynomial, right? Does that make sense, what I'm trying to say?
Yes, sir.
Yeah. So that means that if I say that at some point, this guy, goes to 0, depending on which solution we are looking at, then we have, for some value of n, if this goes to 0, then we have a natural truncation to the series. So in other words, we can say that, let 2n minus lambda minus 1 be 0, and in other words, say lambda, if lambda is equal to 2n plus 1, then the series diverges, okay? So now if I go back to my definition of lambda, see that lambda was given by energy equal to lambda half h bar omega. So this means that the quantization of lambda means that energy itself is going to be quantized. And the quantization of energy is going to be n plus half h bar omega, okay? So we see that from requiring that our wave function is bounded, does not diverge, gives us a quantization of energy, okay? So this is a very, 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 very famous formula, okay? So this is the quantization of energy, okay? Now, for the ground state, E of 0 is half h bar omega. So this is known as the ground state. So we see that for the ground state, the harmonic oscillator, the energy is not 0. And if you think a little bit, you can show that this is actually demanded by uncertainty principle, because if your energy was 0, then it would mean that your momentum was 0, and then your position, your position would not be constrained, and then, but it's a bounded system, so you want your position to be constrained, and therefore you get a contradiction. Okay, so, okay, let me make some comments before we look at the solutions, the energy, the eigenstates. But okay, but do you have any questions so far? I mean, did you guys get did you understand how we got the quantization of energy?
I have one question.
Yes.
So why did we take n to be very large? What does that signify?
Right, that's a very good question. So, these polynomial solutions that we got, right? So the series solution, not polynomial. The series solutions we got, if they went on forever, by saying we take n to be large, what we are doing is that we are looking at this series, but for very large n, right? So we know that if this series was infinite, if series never terminated, then for large values of x, the series, the value of phi would be dominated by large values of n.
Yeah, makes sense.
Right? Yeah. So that's why we took very large values to look at the asymptotic behavior of the series, and we found that the asymptotic behavior of this series is a divergent exponential. It's an exponential of this form. Sorry, not this form, this form. And if you multiply this to the other exponential we already had in our ansatz, this exponential, because it has minus half in it, is not strong enough to overcome this. So the only way to get rid of this divergence is to allow for the fact that this series that is not an infinite series, but it is at some, for a given solution, it terminates. But if I say, okay, how do I terminate a series? Just 1 second. Excellent. Hello? জি কোথা থেকে? ও আচ্ছা, ওটা দিয়ে যান, নিচে দিয়ে যান। আচ্ছা, তাহলে কেমন আসতে হবে? কোডটা কোথায় পাঠাচ্ছে? আচ্ছা, হ্যাঁ হ্যাঁ পাঠান, আমি অলরেডি ক্লাসে আছি, আমি এখন আসতে পারবো না, পাঠান। হ্যাঁ হ্যাঁ ভাইয়া 27606 606। ও আচ্ছা, কি এক সেকেন্ড, আপনি পেপার ফ্লাই থেকে আসছেন তো? এক সেকেন্ড। ও আচ্ছা, হ্যাঁ আসছে। এটা হচ্ছে গিয়ে 6746 6746। জি ওকে, থ্যাংক ইউ। Sorry about that. I get a delivery, so let me.
না না নিতেছ না, এখনো ক্লাস শেষ হতে দেরি।
Okay. Okay, so can you guys see?
Yes, sir.
Yeah. So basically, the only way that we can truncate these series for some value is that if the numerator here goes to 0, right? So that means that we set this to 0, so 2n, and that means that lambda can take only discrete values. So that's why I'm putting a subscript on n. So this is for some given n. It will depend on the solution. Maybe let's call it n prime. So for some value of n prime, and then if I put this back into the energy, then I see that the energy is also quantized. Okay, so this comes from. Let me just make the comment. The comment is that quantization of energy is obtained by requiring that the wave function does not diverge. Okay. All right. And number 2 is so for large n, this means that the energy is of the form of n h bar omega. Okay. So does this formula seem familiar to you?
Planck's
Right. This is the Planck hypothesis. Right. This is precisely, right? This is precisely the Planck's hypothesis. So what Planck said, that the atoms in the black body, they have vibrational modes, but the energy of their vibrational modes is quantized in units of h bar omega. Okay, and we see that we can think of, say, we can, we know from classical statistical mechanics that, you get van der Waals force and stuff like that. And, near the equilibrium, near point, as we, this is, of course, can be approximated by a quadratic potential, right? And therefore, this is something we can assume for the vibrations of molecules as a generic formula, right? So this analysis confirms Planck's hypothesis, right? Okay. And then number
Sir.
3, yeah?
So the fact that we're trying to avoid something diverging by quantizing it reminds me of what we did in the blackbody radiation spectrum. Is this related to that? There was a function that was spiking to infinity near 0, and
yeah,
then
but there,
we showed,
yeah, we have something physical diverging. It is analogous, but I'm not sure if this is exactly the same. This is analogous,
okay.
right? Yeah. So it is analogous, but here it's a constraint that comes from the foundation of the theory, right? It is analogous, but I'm not exactly sure if I would call it the same. Okay? Yeah, you have to be very careful with analogies. Okay. Okay. So 0 point energy. So the 0 point energy is E0 half h bar omega. And this is the energy there at in the vacuum. We don't actually have to do anything with it. We cannot make it, put it to any kind of use. It's just there. And in everyday physics, this doesn't have a big role to play. But it does have a role to play in cosmology. When you study quantum field theory, you will see that quantum field theory can be thought of as an infinite collection of an infinite number of coupled harmonic oscillator. In that case, the quantum field will have an infinite amount of vacuum energy. And there are some ways of regulating that infinity, but the regulation of that infinity leaves over a finite amount of the vacuum energy. And the cosmological constant, the positive cosmological constant, is a candidate for the vacuum energy. Okay, but there's a problem. The problem is the cosmological constant that we observe in the universe is tiny, whereas the vacuum energy that is predicted by the standard model of quantum field theory is of 10 to the power 6 times larger. And this is, in some sense, one of the biggest theoretical problems in one of the biggest unsolved problems in theoretical physics right now. Okay. So, why is the vacuum energy so small? Okay. Okay. Any more questions before we move on? Okay, I think I will need another class. Okay, so because I want to do, okay. So let's look at the solutions, okay? The solutions. And the solutions are given in terms of the Hermit polynomials. This is the same Hermit for whom we have Hermitian. Okay, so what are these phis? So we have phi 0 or phi 1, but we can call them phi n. So these are given by the Hermit polynomial. So our solutions are going to be hn of x e to the power minus half of x squared. Okay, so this will be the form of our solution, and there is some normalization constant like C of n. Okay, so now you can work out what these are. So for the zeroth energy, for E equals to n equals to 0, the Hermit is, just using our recursion relationship, you can work this out. For h1 of x is 2 of x. This is an even function. This is an odd function, right? Even, odd. And then h2 of x is 4 of x squared minus 2, even. Then h3 of x is 8 x cubed minus 12 of x, and so on and so forth. Okay. So I want to say a few words about the properties of the Hermit polynomials. So the Hermit polynomials are solutions to the Schrodinger equation. So called now, but in this context, we're going to call it the Hermit differential equation. H of n minus 2 of x, h of n prime plus 2n h of n equals to 0. So what's happening is that we are putting, in the Schrodinger equation, we are putting a particular value of lambda. Okay, so this is for n positive integer. Okay, right. The Hermit polynomials, it's not hard to show, that satisfy okay, let me just satisfy the following. Recursion relationship. So, for example, the first derivative of hn is related to hn plus 1, hn plus 1 minus 2x, hn plus 2n, hn minus 1, 0, and number 3 is h of n plus 1 is 2x hn minus h prime. H prime of n, I think, or n minus 1. Yeah, I'm not sure. It's probably n. Okay, I'll have to look it up. Anyway, I think this is kind of beside the point. So there are lots of infinite number of Hermit polynomials. So I wanted to introduce the idea of generating function. It's a very useful idea in mathematics as well as physics. In physics, if you have done partition functions, thermal physics, this is the analog of a partition function. So what does a generating function do? It generates all the Hermit polynomials. Okay, so okay, before I say that, let me just make another comment about the Hermit polynomials, is that the Hermit polynomials form a complete basis of functions. Means that any one-dimensional function with some well-defined properties like L2 integrable functions can be, any function can be expressed in terms of Hermit functions, okay? In terms of linear combination. This is similar to, so this is analogous to this thing, right? We saw that Fourier told us that e to the power plus minus ikx, we don't actually have to have plus minus because k can take both signs, that these are complete functions, right? Any function can be expressed in terms of linear combination of them. The Hermit they also have the same property, okay? This is not as well known, but they also have the same properties. Okay, these are just mathematical tidbits that kind of I wanted to tell you because in case you're interested, they're not really into relevant in our course. Okay, so I wanted to tell you about the generating function. So if I ask you, can you give me Hermit number, say 132 of x? Then there is a function which is a function of x as well as an auxiliary variable h, which is defined as n goes to 0 to infinity. The coefficients all are the nth Hermit, and it's h to the power n divided by factorial of n. Okay, so this is there's a way to figure this function out. If you derive this function, you can figure out any Hermit polynomial. And I'm not going to show you how to do that. It'll be in the notes, but you can essentially show that g of x of h is given by e to the power 2xh minus h squared, okay? So this is a very useful function because if I have this function and I expand it, then the relevant coefficient of h is going to give me the Hermit, the appropriate Hermit functions, okay? Okay, so I'm just going to talk about now the wave functions and the Hermit. So in quantum mechanics, we are looking at the wave function psi of n, and its normalization for the Hermit is going to be 2 to the power n factorial square root of pi, and there's this thing, and minus e to the power x squared by 2, of course, and the hn of x. So this is what our wave functions look like. And from the normalization, and you can show that these energy eigenstates satisfy the orthonormality relationship, okay? And let me give you some of the fundamental, some of the low-lying wave functions. So for example, the lowest one is a Gaussian, because as you can see, H0 is a 1, right? Remember? H0 is 1. So we are multiplying it with a Gaussian. And this is our full wave function. So this is 1, so this is a Gaussian. So our ground state wave function is something like this. So Gaussian. Okay. So the second one is going to be, we'll have this form. Okay. And this fits in nicely with the discussion we had about one-dimensional wave functions. And these are, as you can see, v of minus of x is v of x. So this is a potential which has, which is symmetric, and therefore the wave function will have definite parity. Okay, so this is the ground state, psi 0. This is psi 1, and this has one node, and then psi 2 is going to be, oh no, this is not in the asymptotic limit. Nyan asked a question. So no, Nyan, this is not asymptotic. This is exact wave functions. Okay. So this is going to be psi 2. Okay. So on and so forth. Okay. All right. So this is what the solutions of the harmonic oscillator look like. But classically, like, let me tell you something about the classical limit. Okay. So classically, if I look at a classical harmonic oscillator, then if I say, okay, where does it actually spend most of its time? If this is like the boundary, then you can actually figure out that the harmonic oscillator particle spends most of the time. This is going to be the probability distribution for the classical harmonic oscillator. And if I look at very high values of n for the quantum harmonic, so this is classical, okay? This is the classical probability distribution. Now, if I look at a very high value of n for the quantum harmonic oscillator, then you can show that its probability distribution is going to be looking like this, okay? And you can also figure that out from the mnemonics that we discussed. Okay, so for the large n limit, the quantum harmonic oscillator, the probability distribution does approach that of the classical distribution. Okay, so I think I'm going to end the discussion of the first part of the harmonic oscillator here. Do we have any questions before we move on to the second way of looking at the harmonic oscillator? Sorry, I went a bit quickly towards the end because I don't think those are very important things, but let's just open it up for discussion. Do we have any discussions? Because we won't be able to finish this class today anyway. So we will need another class. And I will post the problem session video tonight. Sorry, after last night's problem session, I became really ill. So do you have any questions, comments?
Sir, what's this classical limit that we're talking about here? Like, how does this correspond?
Yeah, that's a very good question. So if you have suppose that we have a harmonic oscillator, right? So this is a classical harmonic oscillator, right? So, we can say, okay, this is so this is going to go like this, right? Now, if I say, okay, how much time does this bob spend in this area as opposed to this area, right? So the more time the bob spends in this area, the bigger the probability you have of finding it there, right?
Yeah.
So this is the probability density for that, okay?
Oh, I see.
Because it's going fastest at the bottom, it spends the least time.
Exactly.
Okay.
So yeah, so that's the thing. And so this classical behavior is not obvious from the wave function, the ground state wave, the low energy wave functions. But if you go to the high energy wave functions, then it becomes more and more obvious. Okay. Any other questions?
No, sir.
Okay. All right. So I think we have about 20 minutes left. So I want to discuss the harmonic oscillator in a different way, completely different way. Okay. Okay, so Dirac. So in the previous approach, we solved the harmonic oscillator. We converted the Schrodinger equation into, we found the solution of a ordinary differential equation, and by imposing boundary condition, we found the energy eigenstates, and then by solving the differential equation, we found the Hermit polynomials, and the Hermit polynomials multiplied by the exponential give us the solution, right? So Dirac found a different way of looking at these harmonic oscillator solutions, which is a very interesting way of looking at it. So let's start with our Hamiltonian again. So our Hamiltonian is p squared by 2, is minus h squared by 2m p squared. Sorry, not p squared. Sorry. Our Hamiltonian is, in terms of operator, p squared by 2m plus half. Instead of k, let me write it in terms of omega. It's m omega squared x squared, right? So we already showed that this is a positive definite operator, right? We showed that psi h of psi is a positive definite. Now let us introduce some non-Hermitian operators. Okay? Let's introduce two non-Hermitian operators. We shall call it A and A dagger. So A is a linear combination. This is just a constant. It's a complex linear combination of X and P. Okay, so this is A. So because of this I, this is not a Hermitian operator. A is not a Hermitian operator, okay? And then A dagger is m of omega by 2h bar x dagger. X dagger is just x, but I dagger is minus I. P dagger is P, m of omega, right? So these are Hermitian conjugate of each other, right? Is that clear?
Yes, sir.
Now, I have not put emphasis on this, but there is a fundamental commutation relationship that is somewhat fundamental to quantum mechanics. And that fundamental commutation, sorry, relationship is the commutator of X and P is I H bar, okay? As well as X of X is 0 and P of P is 0, okay? So we can prove this very easily. So for any wave function psi, if I apply to it the commutator of X and P, so in the positional representation, X is nothing but just the number X, P is H bar by I, D by dx of psi, minus P is H bar by I, D by dx times X of psi. Right, so here we have X H bar by I, d psi by dx. Here we have H bar by I. First, this guy acts on this thing, so we just get psi, and then we get H bar by I, x of d by dx of psi. And then we see that these two terms cancel out. So we have left over minus h bar over I of psi, right? So if this is I of h bar of psi. So we see that because psi was arbitrary, so this is true for all psi's. In other words, this is by definition an operator equation. Okay, so this is known as the fundamental commutation relationship. Okay, so all other relationships, almost all other relationships in quantum mechanics can be derived from this. Okay. Okay, so we can now use this fundamental commutation relationship to ask what are the algebra of these guys? You know, meaning that what are the commutation relationship of this? Okay, so we want to compute, say, A dagger. So A dagger is m omega by 2h bar. There was a square root in each of these guys. So we now basically can get rid of, that means that there won't be a square root here, right? So, and then inside the commutator, we have x plus I of p divided by m omega, and there here x minus I of p by m omega. Okay? So what we now know is that x will of course commute with x, p will of course commute with p. So of the 4 terms we were going to get, 2 will be 0. So we have m omega by 2h bar. So, and then we have minus I by m omega, and then commutator of x and p. And then we have I by m omega, commutator of p of x. Okay. So here we see that m omega will cancel. Okay. And then we have, from the first one, we have minus I by 2h bar. X and p is going to give us h bar I. And from the second one, we have plus I by 2h bar. And from this guy, we are going to get minus h bar I. Okay, so that means that this h bar will cancel with this h bar, this h bar will cancel with this h bar, and I squared will give me a minus 1. So we get minus half, and here we get I times, we get a minus half, so we get plus 1. In other words, we have A dagger, their commutator is 1. Okay, any questions?
No, sir.
So it should be easy. So AA, because all operators commute with themselves. So AA will be 0, A dagger and A dagger. Commutator will be 0. Okay. So now let us define N. N is a operator which is A dagger A. Okay. So this is, it's not hard to see that the Hamiltonian H can be expressed as N plus half times H bar omega, okay? Now, also it is obvious to see that H of N is going to be, they're going to commute, right? So that means that if psi is an eigenfunction of H, then it is also an eigenfunction of N. Okay? So how do we do this? Say, suppose that we have an eigenfunction of H, which gives us E of psi. Okay, then if I say, okay, okay, to prove this, I think what you have to do is that, yeah, so if you have n of psi, and you apply to it h, so h of n of psi, this is equals to be, going to be n of h of psi, right? By definition, because they commute. And then this is going to tell me n of E of psi by using this equation. And then I'm going to get E of n of psi, right? So we see that n of psi is also an eigenfunction of h with the eigenvalue E. And if the system is not degenerate, then that means that this wave function must be proportional to the wave function psi. In other words, we can write n of psi is some number, some, you know, some eigenvalue curly n of psi. Okay. So this is a general result, is that if two operators commute, you can find simultaneous eigenfunctions. Okay. Is this clear what I did here? Should I go over it again?
Yes, sir, it is clear.
Okay.
Yes, sir. Yeah.
All right. Anyway, the notes will have more detailed stuff. Okay. So, right. So we found that H can be expressed in terms of n. Okay. So if we now find an eigenfunction of n operator, by the way, n is a Hermitian operator. N is a Hermitian operator because if I do A dagger A, if I take the dagger of n, this is A dagger A of dagger, but we know that taking the dagger changes the ordering of the operator, so we get back the same operator, right? So n is a Hermitian operator. So suppose psi of n is a eigenfunction of n with eigenvalue small n. So for now, this is just a number, real number. It doesn't have to be an integer, but we'll see eventually if it is a positive integer. If I do this, then the Hamiltonian acting on psi of n is going to be n plus half h bar omega acting on psi n, n plus half h bar omega acting on psi n. So that means that psi n will be an eigen function of h with energy n plus half h bar omega. Okay, so now we have to find out what n is. If we find out what n is, then we have solved the problem. Okay, do you understand? Do you agree? Okay, I think I'm gonna end here because otherwise you're just gonna get some overload, sensory overload. So maybe we can have one last class tomorrow evening. Is that okay?
Fine by me, sir.
Like maybe around 8 tomorrow. Is that okay?
Yes, sir.
Yes, sir.
Okay by me.
Actually, just be on call because I have a meeting at 4. So maybe let's do it 9, because I think I have a meeting at the other end of town at Lalmatia. So it might take me a while to come back. Okay. Okay, any questions? Okay, I'll be posting some lectures tonight, okay?
Okay, sir.
And tomorrow what I'll do is that I'll start again from the beginning.